It's on the, yes.
Not that I didn't put the other one. Wednesday, 25th, PowerPoint. There's two, it would be the second one. Thursday.
Said there was a street thing, but not anyway.
What is it that they need?
Huh?
They need
It says
what?
there were each
I know,
classification.
but those that are free floating, what do they need specifically to make their food?
Doesn't say on the notes.
We didn't say anything about sunlight.
No.
Photosynthesis.
On the notes.
Yeah, it should in photosynthesis. It should say photosynthesis, and they're going to be near the surface. So that is free floating near the surface.
I don't see it.
We'll go over in just a minute. I just want to so give me just a second. We'll go over it, you know, when you submit claims. All right, so plankton, that's the first one. So your text box, if you haven't already typed it, type plankton. And floating. And if you're floating, you need to be mostly near the surface, because most of them photosynthesize. That's plankton. All right,
Um,
where are they found? Look on your paper and for me because you were here.
is what?
Benthos.
Any form of ocean body that lives on the ocean floor.
Four. Then we have Neptune. I spelled it right. I already used it. And Neptune are what?
They're freely.
All right, they are free swimmers. They'll go anywhere.
They can use they can use the ocean currents if they want to. They just like
We
turtles.
call free swimming. So pretty much you find between the surface and bottom. So free swimming. Not bottom dwelling. They're not floating on the top, but they can move on their own. All right. So in your notes, find a part. We're not doing anything right there. Go away, go away, go away. Um, find the section that says temperature and salinity. So that's here. That you're going to take your packet. You're going to close up your top page and flip it all the way to the back. The top page. Flip it all the way to the back. Temperature. So you've been working there. You're going to continue working there.
Yeah.
You'd already started on it there.
Yeah.
Okay. Um, all right, so we're on the temperature and salinity part. You're going to fill in as we talk about it. Um, so, sunlight. Hold on. Wait, the surface supervision. Okay, so in the first blank, you're going to put sunlight heats the surface. So, sunlight heats goes in the first blank. So, the surface is going to be much more, and it is heated by the sunlight. And so based on temperature, we have three zones. We have the surface zone, and this is going to be the warmest, and it's going to go from sea level to about 300 meters. This is, thank you. It can penetrate a few meters, but the wind and waves mix this heat evenly throughout the zone. So the surface is made the same temperature zone. Heat line is usually think of it as a boundary. And this is going to be, and also think of it like decline. It's going, something's going to change here. So this is going to be marked by rapid temperature change with depth. So the temperature is going to change very quickly. And this period, this distance that it changes quickly is called the thermocline zone. This is going to be between 300 and 800 meters below sea level. Then you reach the deep zone. So this is 800 meters to the floor. And this is going to be where temperatures will continue to decrease slowly. So the deeper you get, the colder it's going to get. You should have those filled in. And you see kind of a picture there that shows you that the surface zone stays pretty much the same. But as you approach the thermocline, it's starting to cool off. Then the thermocline cools off very rapidly. And then you've got a slower cooling in the deep zone. Everybody got blanks filled in that section through deep zone. Temperatures for deep zone continue to decrease slowly. All right, so what is in the ocean water? That's the next little section at the bottom, and your picture kind of didn't copy here. Um, I don't even think it showed up over there. No, this one didn't show up at all. You just see the very top of it. 96.5% of the ocean is water. The rest is dissolved gases and solids such as salt, with sodium chloride being the main salt of the ocean. So you're going to put 96.5% in the first blank. The second blank is 3.5%. And so here's a sort of a picture. So you have the majority being water, but within that, of these dissolved gases, you've got 30% of that 3.5% is sodium, and 55% is chlorine. Those two together make sodium chloride, which is salt. Magnesium, you have about 7.7%. You've got some sulfur, you got some calcium, you got some potassium, and then you have others. This is smaller percent. So there's a lot of different things that are in with that water. So that 3.5% makes up a lot. Salinity is a word. Salinity starts off as like salt, so think salt. So salinity is the amount of dissolved solids. So you take this is at the bottom of that page we're on. The amount of dissolved solids is what you put in that blank. And it's mainly salts that you find in ocean water. So salinity is a property of ocean water, and we can measure it. And about 35% of the ocean water is, or that's parts per thousand, is going to be, is your salinity. So that symbol here is a new symbol. It's parts per thousand. So 50 million billion tons of salt is in our seas. So that's how much salt is in our seas, and the majority of the ocean is also water. Think about how much water that is.
Bigger than million?
Yes, but million billion means it's even bigger than a billion.
billion million.
No, it's like 10,000. 10,000 is 10, comma, 000. All right, 1,000 grams of seawater consists of 35 grams of dissolved salt. So that's what this up here means right here. If I take 1,000 grams of seawater, within that 1,000 grams of water, seawater, is going to be 35 grams of it is going to be dissolved salts. The rest is water. That may have to flip your paper over there. And that is at the top of the next page that looks like this. That's where we should be. So we should already have filled in the first bullet on this page here. And this is dissolved salts is the first blank. The next blank that you come to is this down here that's bolded. 35 grams in that blank. I'm getting ready to move on. Right, so if you see this image here, you've got the darker it is, the more salts per thousand, or the higher that number is. So if you notice, the Atlantic Ocean has quite a bit, with right in here in the middle having the most. Over in the Pacific Ocean, it's down near in between Australia and South America. And then on the other side of South America in the Atlantic Ocean, from what this section of the map here, looks like there's another section to the east or west of Australia. And then the lighter it gets is the less salts. So what do we know that kind of flows right through here? What is this area called on a map or line of latitude? Equator. So these ocean waters here that seem to be saltier must be what? Closer to the equator. They're warmer. So it appears warmer water is going to have more salt. What's going to happen to the water if the temperature is increased? What change of state is going to happen? Evaporation. So if it evaporates, the salt doesn't evaporate, it's left behind. So these areas are probably areas that have more higher temperatures, so there's more evaporation that takes place. Notice the further north you get or the further south you get closer to the poles, there's not a lot of salt.
And it says packed ice.
Well, yeah, when you get to a certain point, it's ice. All right, so down here's what we're filling in. Large amounts of evaporation will increase salinity. Evaporation will increase, goes in that blank. The second one, large amounts of precipitation. That's any type, rain, snow, sleet, hail. Melting ice and runoff from land will decrease salinity.
So what would happen if there was no salinity at all?
It would be pure water. Even, well, it's mostly talking about salts, but there's even stuff in fresh water. So it'd be more like fresh water. All right, we got those blanks. Okay, the next one is precipitation, melting ice, and runoff. Decrease. The next blank, precipitation, melting ice, all right. Salty. So pretty much rivers will empty into oceans. As rivers flow, they're picking up minerals, they're picking up other substances as they flow, and it empties into the ocean. And so there's where uh, salt enters. As water evaporates, salt is left behind, and the salt is going to be left behind in the ocean. And so what you're going to fill in is the principal source of dissolved salts is in the ocean is the weathering and erosion of rocks on land. That's what you're putting. Weathering and erosion of rocks on land. Since the oceans were first formed, they've been getting saltier. Now more salt is being deposited on the ocean floor as it's coming from rivers and reaching a general equilibrium. So remember, I don't think we talked about it in here, that's physical science, that you can only dissolve so much salt in water, in a certain amount of water. And what doesn't get dissolved will sink to the bottom. And so that's what's happening as more and more salt is being deposited or getting into the oceans. If it can't dissolve it, it's going to sink to the floor. So weathering and erosion of rocks. Enough. All right. So there's something called desalination. So a lot of people are saying, well, why, since we need water, why can't we use the ocean water? Well, we can't drink salt water. We have to take the salt out first. And to say take the salt out, it involves these huge processes at the coast where they take the ocean water and it goes through a process of desalination to remove the salt. And it's a very expensive process.
Why can't you do it that way?
Doesn't it make you
Well,
look like
technically you
hallucinate?
can if you build something
Oh.
to purify it.
What I just said.
I mean, a homemade thing.
It's very expensive to desalinate water. You can't
Just I don't know
afford
why you can't drink it.
It makes you hallucinate.
it.
And then doesn't it like dehydrate you?
It will dehydrate you, and then it also will make you throw up because the
I'm
imbalance
gonna try that one day.
of the, you get too much of the sodium ions and chlorine ions in your body, it's gonna mess up how your systems work. All right, desalination, you should be writing the definition. It's been up here. You need to be writing, taking the salt out of water. Taking the salt out of water.
No.
Taking salt out of water.
That's my reindeer name.
Unless you're a squirrel.
BD rocket burger. Oh, yeah, that's good.
All right. We also have another problem,
I like problems.
with ocean and pollution, and it's called ocean acidification. That means the ocean is getting more acid in it. And here's sort of a picture diagram. We have all these factories just putting pollutants up in the air. And then these pollutants, when it rains, are going to be dissolved into the rainwater, and it's going to come down, and the acid rain will destroy forest, and runoff from that gets back into the ocean. So that's sort of the flow that's going here. So what happens? Look at that. It's excess of carbon dioxide from the atmosphere will get into the oceans. The oceans are a sink for atmospheric carbon dioxide. That means it's like a storage place. So the oceans are, you're going to write, a sink for atmospheric CO2. CO2 is carbon dioxide. Carbon dioxide increases the acidity of ocean water. What happens is it's going to combine with the water, and it's going to create an acid, carbonic acid. So the next blank, carbon dioxide increases. Next blank is increases. And then the third blank, ocean organisms suffer, especially from calcium carbonate, or especially the calcium carbonate organisms. These are organisms that have shells. Acid is going to cause those shells to deteriorate. Organisms. Last blank. Ocean organisms suffer. So things like clams, oysters, their shells deeper and softer because of the acid that's in the oceans. What's wrong with it? All right, so pH is disrupting the shell formation. So if these organisms do not have their shells, it's going to have an impact on some of our fishing industries here. So economic losses goes in the first bullet. Economic losses. We're in the negative impacts. First bullet. So fisheries, these are people who go out and fish for the scallops, fish for the oysters, fish for any of the shellfish that we would eat. If they're not producing their shells and have their hard shells to survive, to grow, to mature, they're not going to harvest, to sell. We're going to have a decrease in global shellfish production. And just so you know, in the U.S., that's about 10.5 billion US dollars that we make off of this, that we would be slowly losing. It's going to disrupt livelihoods. We're going to need less of this industry if the product disappears. So it's going to cause people to have different jobs. I believe that is it. You have economic losses? Okay. Then we're going to open up the next one here. We're going to look at currents and climates. So you're going to take your paper and you're just going to flip it. You're doing the paper. And so we're going to first look at ocean currents. These are sort of masses of water that are going to flow from one place to the other. And here's sort of a picture of a couple ocean currents there. They can be on the surface or deep down in water. So you need the definition right here. Masses of water that flow from one place to another. Masses of water that flow from one place to another. They can be on the surface or deep. Water that flow from one place to another. All right, so ocean currents are going to move water. So if you were to set one of these little duckies and follow it, so look right here, 1992, 29,000 ducks left China and fell off a boat in the Pacific Ocean. 10,000 drifted north. 19,000 went south and washed up in Australia, Indonesia, and South America. All right. Notice the ones up north went up here and eventually came down here. 15 years and 17,000 miles later, they came up on the British beaches. So notice it took them following the currents that went north 15 years to get back over here in the Atlantic Ocean. So just something to kind of think about, and that was just following the currents. All right, so in the next section, surface currents. We need a definition right here. Movements. Well, movements of water that flow horizontally in the upper part of the ocean. Movements of water that flow horizontally in the upper part of the ocean's surface. Right here. Movement, start with movements of water that flow
Oh,
horizontally. I guess you could stop there because it's obvious we mean in the upper part. Movements of water that flow horizontally in the upper part of the ocean's surface. And the energy that drives this, if you can fill in that blank, comes from wind. Wind. Comes from wind. So surface currents, the energy is like gyres. I don't know how to say, you know how to say that?
geysers.
No. Should we ask it? Gyres, I think. No, we don't need to look it up. Are large whirls of water within the ocean basin. So these are kind of like convection currents. So you've got a cold current and a warm current. And the circle that it makes is what this is. So you have one in the North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian Ocean. And this is going to be due, and these flow this way because of a couple reasons. So the definition is up here at the top. Large swirls of water within an ocean basin.
These are not the exact same one. Like there's
Okay, I'm not worried about the picture being the exact or not the exact. Right now, you need the definition. Large whirls of water within an ocean basin. They're still showing the same circular patterns. The maps are just different. You don't necessarily need to write what's in the bullets. You just need that definition. All right, we're going to look at why they move in a circular pattern. And there's two reasons. Number one, or the main thing is the rotation. Just like the winds, the rotation of the earth is going to deflect these currents, and they're going to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. So, in the first blank, deflected to the right in the northern hemisphere, you can abbreviate northern hemisphere NH, and to the left in the SH or southern hemisphere. We know this process as the Coriolis effect. So not only does it affect our winds and our air masses and deflect them, it's also our currents. So to the first blank, right in the northern hemisphere and left in the southern hemisphere. The other thing that's causing them to move is as water cools off, it sinks, and then as it heats up, it rises, and it creates what we call a convection current. So these currents, what they're going to do is they're going to keep a balance of energy. They're going to keep cycling ocean water from the equator to the polar regions. So at the polar regions, the water is cold and it's sinking and it's moving down toward the equator. At the equator, it heats up, it rises, and it's moving as it moves up to the poles. So, first blank, oceans maintain the balance of heat energy by ocean currents cycling between equator and polar regions. Equator and polar regions. Equator and polar regions. Currents from the low latitude regions must move into higher latitudes. They transfer heat from warmer to cooler areas in Earth. The first blank, equator and polar regions. In polar regions.
Alright, I'm on the small one. I don't know.
Just hold you. So you're ahead of where I'm at,
Yeah, wait.
and you're gonna have to wait. All right, then the second bullet. They're very important to coastal regions, and here's the reason. They're going to warm or cool the air temperature. They're going to warm or cool the air temperatures. So along our coast, we have the Gulf Stream. That's a warm current. So we're going to have warmer coastal temperatures. And this actually warms some of the climate of Great Britain because Great Britain is way up here in the north. And so as the stream goes, Gulf Stream goes, it's going to warm those areas. And what you're going to put here, for example, is the Gulf Stream, which warms the climate of Great Britain. Gulf Stream, which warms the climate of Great Britain. And get Great Britain up, Great Britain, and then you're ready. He'll be on as soon as he writes these two words down. Leave that paper here.
I have some things.
All right. So you can kind of see temperatures here. And notice you have warmer temperatures down toward the equator, and they slowly are getting cooler as you go up. All right, now we're on deep density currents. So your deep currents, here's the definition. Vertical, so surface or horizontal going this way. Deep are vertical currents going this way. So these are going to result from density differences among water masses. So warm water is going to be denser. So I believe it sinks. I have that right because it has more of the salt, and then it's going to rise. To get the definition written, factors that affect the density of seawater is going to be water temperature and salinity. And my picture kind of interrupts this statement that's on your paper. Decreasing temperature and increasing salinity cause water to become more dense. Oh, so I had it backwards. Cold water sinks, hot water rises. Sorry about that. And you're going to flip your paper. Guessing you guys are through this part here. Camden, you've got this? Okay. So, deep currents. Near Antarctica, surface conditions create the highest density in the world. Um, so, evaporation results in increased salinity. So, it's going to increase water density. And this sort of creates what we call a conveyor belt because you've got water that's slowly moving, like that image with the little rubber duckies, that's slowly moving. As things follow the current, eventually they will be moved around in these currents. Upwelling. This is where cold water from deeper layers replace warmer surface water. And so when this happens, it's bringing food that, I'm trying to remember if it comes right, it's coming, cold water is moving up. And so the warm water that may have less nutrients, so the cold water is bringing nutrients up and pushing the surface water down. And this is where places where there's upwelling, you're going to have a lot of fish there because that's where a lot of the nutrients is going to be. So winds blow the warm surface water away, and then it's going to be replaced with the colder water that has lots of nutrients. Therefore, this is where you're going to find lots of fish. So if you were working for a fishing company, you'd want to know where these places are so you could go and get the fish. So deep water is very rich in nutrients and is brought to the surface at upwellings. Basically, it's revitalizing the ocean and keeps the ocean healthy. And if we come along and we are getting all the fish and all the nutrients that come in those areas, then we're getting it out of balance. So it's a way that keeps the ocean healthy. And we're not dealing with these questions here because we're not doing that. All right. Waves and the shore. This is the last little section we're going to try to get through today. So, waves are just the ocean energy traveling along the boundary between the ocean and the atmosphere. And the power of the waves is most noticeable at the shore. So that's why we're going to kind of look at this. One group of long rolling waves is a swell. So you had to put a definition for swell. It's a long rolling waves. So that's what you see in this picture. There are three things about the size of a wave that can affect it: how the speed of the wind, the length of time the wind blows, and something called fetch, which is the distance the wind blows. So you need to have those three things in those blanks. So if we go to wave terminology, you have the crest of the wave, which is the highest point. You have the trough, which is the lowest point. Wave height is the vertical distance from trough to crest. And wave length is the distance from one crest to the next. So the wave length is usually 2 to 3 times the wave height. You need to be familiar with some of these terms here. Waves break in water that is as deep as 1/2 the wave length. So energy in a wave, as a wave moves across the surface of the ocean, only the energy is moving forward, not really the water, even though that's what it looks like. Now, breakers is that foamy mass of water that will wash onto shore. If the ocean floor is steep, it's going to break with great force. If the ocean floor is not steep, it's going to have more spills. It's going to have that slower rolling motion. There are steeper floor off the coast of California, so you're going to have breaking with a greater force than you will on our coast. All right, the longshore currents move. This is the longshore currents. This is movement of water that parallels the shore within a surf zone. It occurs when waves approach the beach at an angle, and this is what forms our sandbars. Refraction. When waves approach the shore at an angle, they will bend when they reach shallower water, and this is refraction. It causes the waves to hit the shore head on. Then we have undertow and rip current. So an undertow is a gentle current that moves water and sand from the beach back to the shore. So if you stood on the beach in the sand and you felt like when the water was rushing back, it was taking the sand with you, that's kind of undertow. Rip current are dangerous currents that flow away from the beach carrying sand and water. And so you want to swim parallel to shore if you get in a rip current. If you're not a strong swimmer, you shouldn't be out in the water that has the potential to have rip currents. Rip currents form when water from large breakers return to the ocean through channels and underwater sandbars. So it's areas that allow where sandbars have built up and there's a channel between. Usually they'll have signs posted when this happens. They'll have warning signs here. All right. Wave, where are you?
I couldn't find, right here.
Oh, so you found that? Found it down. Where are you? Where you at? Are you on the? All right, we're probably gonna stop right there. Yeah, get to where you see this slide right here, which says wave erosion transition. We'll start there tomorrow and finish up with a repeat of some of the times we've already talked about.
So are these the last slides that I have to go through?
Tomorrow there'll be tides that will be done. Not the whole thing goes tonight. And if the due date is late, don't worry about it. Remember what I said. Probably did go faster than we are, but it doesn't matter. I don't count things off late anyway. I will be getting some information to you about what you're
We're doing exams in here.
an email either to you or to your mom.
They gave me mine.
I know that you were here. I don't know if you was here that day.
We stop a lot.
We started with that, I think.
I hate you.
Um,
I'll be glad we spoke about some credit.
the DNR that they,
Jay and Steven. His Jim Matt Martin. No, I didn't get it.
okay,
Martin, you don't have to come.
then if your mom didn't get any, I think you have to come, you still should have gotten a paper.
I didn't get it.
Did you get a paper report? It would have, who's your teacher? Ms. Flint should have emailed you a progress report. I wonder if she emailed it to your mom. Now, Ms. Swear, but you need to go ask Ms. Flint if she emailed her progress report. You have foods, right? You have to come on for food, for food.
First, what, 16?
I think so. Now, for the rest, you'll have something that you'll have to do on that day at home, and each teacher will tell you about. Part of your class next week.
This class?
Yeah, and then you'll have a piece that you have to do at home, okay? So it's kind of two parts. So I have to quite decide what we're gonna do in class. There's gonna be a piece you're gonna do in class. We'll probably work on next week, or at least Monday and Tuesday, right before exams start. And then there'll be a test part that we'll do at home. And we'll finish these notes and probably do a test on this, and then we're concentrating on doing some of the topics we're gonna get to, will be what we will do for, the in-class exam part, and we'll have a test part. I just haven't quite decided what I wanna do. And it may be like a poster or a brochure or slides. It's gonna be something like that that we're gonna do in class. And I'll have a couple topics for different people to choose, and then there'll be a exam. That will cover at least everything that we've done here, like with the oceans and stuff, up through the ocean, so everything from the first quarter through oceans. So I'll pull questions from all the tests and make it an exam. That's kind of where I'm at there. And you have P, right? She'll have something for you to do, and that'll be some type of teacher-made little project. The teacher-made, yes, they may have to do a project. I don't know what he's gonna do. But it's important right now. I haven't had that big assignment since June. You should be pretty caught up.
Yeah, I'm actually looking at it now. I still have a lot of stuff to do with Jim. Oh, man.
You need to make sure you're working on it at home now.
I know.
I'm sitting here recording, and we're not doing anything. Edit, keep editing.